and introduce Brian Fath, Townsend University, and IASA, who will be talking about Quo Vadis ecosystem, insight from the ecological modeling and systems ecology. Brian.
Thank you, James. Thank you, everybody, for the invitation to be here. It's my first time at one of these meetings. I'm one of those new focus research groups. It was just mentioned, or I should say part of one. I'm not the focus research group myself. Yeah, we had 20 members, I think, according to that, and we're doing some more heavy reach out. So hopefully those numbers will be changing. So yes, I am a professor at Towson University, which is in Baltimore, Maryland, and I also am a research scholar at the International Institute for Applied Systems Analysis in Luxembourg, Austria. And so I actually was coming from Vienna, and I'm going back to Vienna on Thursday, not from Baltimore. So yeah, I'm only here for these first 2 days, unfortunately, because I needed to get back to Vienna. So just briefly, the International Society for Ecological Modeling is the co-sponsor of this new focus research group. The society is about 40 years old now. It was founded in conjunction with the journal Ecological Modeling, which was having its 40th anniversary this year. It was founded in 1975, so it's actually one of the early ecological suite of journals within that suite. We have about 300 members. It's based on conference attendance, so if you come to a conference, you're a member, and we have conferences, global conferences every 2 years, and we have chapter conferences kind of on the off years, particularly the European chapter is quite active, and the Asian chapter as well too, and we just formed an African chapter. So it's quite a busy group. And so on the way of making announcements, let me give a plug for the next global conference, because I'm actually hosting it at our university at Towson. And so this is going to be May, a year from now, 8th through 12th. And I have a few flyers about this. Actually, there was something wrong with the package, so only 2 of them seem to come through. But you can see the website if you, it's down on the bottom right there, isemconference.com, and some of the keywords on Google would obviously take you to it. So I think there may be some interest for some of the people at this conference to participate in that. One other quick plug before I get into the substance is one of the programs that we run at IASA at this research institute in Austria every summer is a independent research opportunity for advanced PhD students. It's a 3-month program that runs from June 1st to the end of August, and you will work with an IASA staff member, under the supervision of an IASA staff member working on an independent research project, and you get funding to do this. So it's, if you're selected for this, there's about 50 students every year out of maybe 300 or so applications, and they then you will receive funding to spend the 3 months in Vienna. Now obviously the deadline for this summer has already passed, but just keep it in mind for any of the students that are out there now, or if you have students that you'd like to promote for this. The deadline is always somewhere in mid-January for the upcoming summer, so you have plenty of time to think about the summer 2016. And I have a couple of flyers about that program as well too. So I hope I don't take any of this stuff back with me. I actually have a few journal flyers. Actually, those came through well. I have a number of journal flyers for the Ecological Modeling Journal if you want to pick one of those up. So, okay. So the talk, I didn't explain the title. I'll assume you all know Latin, so that was obvious what the title was, but it's really ecosystem dynamics. Quo Vadis ecosystem, where are you going ecosystem? How are ecosystems changing? So in theme with what our focus group is titled, I thought it'd be appropriate to say some words about our understanding of ecosystem dynamics and where we are with that. So a basic outline of some of the general topics I'll be talking about there. And the main point is that we're dealing with open systems. And I think we know that these are energetically driven systems, but they have sources, and they also have to have a place where they are putting their waste and their waste heat energy out of that. So we're looking at a system that's embedded in a larger environment. We're dealing with all the boundary issues that can complicate things, but once you identify your system of interest, you are now looking at what is actually going on within that boundary. And the main thing is we see these really cool things with self-organization and complexity, right? Ecological systems are able to take in solar radiation and out of that create this diverse and quite amazing ecosystem out of that. And thermodynamically, we know what's going on is that they're able to take those high-quality energy flows. So solar radiation for plants is a high-quality energy flow. They use it to maintain and create order, and then they give off the bad stuff at the end. They give off waste heat, essentially, back to the environment again. And the constraints that they're dealing with, that ecosystems have to deal with, are first of all the solar radiation constraint, which is a fixed amount of available energy input. But again, we see a lot of diversity, a lot of interesting things that have evolved over 3.5 billion years of life on this planet, with having basically the same amount of solar radiation available for the systems to function. We have other major biogeochemical cycles that are also constraining the amount of development. Carbon cycling, obviously other nutrient cycling, hydrologic cycle. As I was flying in here to Denver yesterday, I don't come west that often, and you see no trees, big sky country, and everything's open. I'm thinking, yeah, I'm in a different biome here, and it's just not enough rainfall to support the kind of vegetation that I have out east. And the only agriculture that you see are the irrigated, the circle crops, because without water you don't get any productivity. And so basically what we've tried to do is take, what worked out east when there was plenty of rainfall and recreate it out here out west. And obviously it's not even as bad here as what we're trying to do in Phoenix and places like that. But the point is that ecosystems, what was here was a very functional, vibrant ecosystem within the constraints of the hydrologic cycle and the nutrients and the solar energy that existed here on this space. Okay, on the output side, it's basically the constraint is dealing with the rates of decomposition and the rates of avoiding unwanted accumulation of byproducts, right? So that the organisms and life can't exist in its own waste, so it has to find somebody else to take its waste and make something useful out of it, or find a place to discard it. So once you've got those input-output constraints in place, and those are really the primary constraints for any system functioning, and even for, I think if you talk about system sustainability as a scientific concept, that's the starting point. You have to meet those two requirements for a system to be sustainable. But then the question becomes, what's actually going on inside that box? Once you've got those two constraints more or less met, and again, we see that ecosystems have evolved and developed within these constraints to make quite amazing structures. And so the research question is essentially, what are the patterns of organizations and complexities that arise within ecosystems? And we know that ecosystems are dynamic, and they're not just changing, but they're changing in a certain direction. So we have this directional change, which is the result of positive feedbacks, which are moving systems further from their starting point. And in ecology, we refer to this as succession, this ordered pattern of growth and development. And what we see as a result of that is a decrease in the internal entropy and an increase in the complexity and order as a result of this directional change. So we're getting more complex systems over time. We're getting more order, more organization. And the textbook example of this is something like secondary succession, where you have a nice ecosystem that is functioning well, but then a disturbance comes in. Maybe it's Hurricane Sandy, maybe it's a fire, maybe it's a tornado, maybe it's humans coming in and clear cutting. But over time, there's going to be a reestablishment of the ecosystem from the remnants of the previous biological community. And in this particular case, I'm guessing this is a laser pointer. It is. With secondary succession, the main difference between that and primary succession is that you've got the below ground established structures in place as far as the soils and the nutrients. And so it can happen relatively rapidly, on the order of maybe a century, to return to the previous climax community, assuming, of course, that there was not so much damage that you've destroyed your foundation for there to be the reestablishment on there. But again, the point is that it goes through these stages, and ecological managers can benefit from knowing these. You can't just skip over these middle stages. You might be able to rush them a little bit through some intensive management, but ecology works at a temporal pace that is reasonable, but real also. Okay, so in general, we can think of the basic logistic curve explaining that we've got, maybe not much going on here in the early stages, and it goes through some periods of growth and development, and then in the later stages, we reach this climax community and this kind of more equilibrium configuration. And so what is going on, let me just back up for a second. I haven't said anything about this axis yet, and that's an important one. What are we actually measuring that's changing? Is it biodiversity? Is it complexity? Is it organization? Are there some things, some extremal properties that we can think about that contribute to our better understanding and management of these complex systems? And if there are these extremal properties, then how are they interrelated and how are they informing us about the system as it's changing over time? There was a seminal paper in Science, 1969, by E. P. Odom, where the title of the paper is Trends to be Expected in Ecosystem Development. And he outlined in that paper 24 different ecosystem attributes. I've summarized about, less than half of them right here, and they dealt with different things such as community energetics, nutrient cycling, and overall homeostasis. And the idea was he was looking at what are these trends, what are these essentially extremal principles as the ecosystem changes from an early development stage later to the mature stage. So for example, with community energetics, the gross production to community respiration ratio is much higher early stages. So there's a lot of additional energy available for growth. In the later stages, the production is quite high, but respiration is also quite high. And so those are approximately balanced, so there's not much additional energy for growth. The gross production to standing crop biomass is also quite high early because there's not much biomass in that early field, but there's a lot of production going on. Most of the material is photosynthesizing material. Later stages, we've got a lot of biomass. A lot of it is tied up in wood or in roots or in soil organisms that aren't actively producing in an ecological sense, but they're consuming, so you get a low ratio there. Biomass supported is quite low for the energy per unit energy, but then quite high. Later stages, we go from more linear to more web-like systems. Our nutrient cycles become more closed, slowing of the exchange rates and better conservation of nutrients. And then some of these ideas about overall homeostasis, that's the greater stability, which we can argue how we define stability, lower entropy, higher information, and so forth. So this is kind of the idea of what we're chasing, essentially. Do these make sense? He was putting this paper out in 1969 as largely a set of hypotheses to be tested, based on his own, already at that time, probably 40 years worth of experience in ecology and his own insights. And now we've had enough time, to look at this and to see that in most cases he was largely correct. That there was a lot of insight that he had. So, for example, if we look at succession in terms of the energetics, a bioenergetic model, again, in the early stages of succession, production is much greater than respiration. So this is the dark line is biomass. So at the early stage of succession, after the fire, there's not much biomass left on the landscape. And the gross production is this curve, respiration is the dotted curve, and the difference then between gross production and respiration is the net production, what's left available for the ecosystem to do work. So in those early stages, when you get a little bit of green plant growing there, then production takes off and there's not much respiration, so there's a lot of additional extra energy that is put into growing the ecosystem, and you get the actual increase in biomass and complexity at that point. In the later stages, the production starts to match the respiration. And, this has been tested that there's some evidence that gross production does actually decrease, but more importantly, what happens is respiration costs increase. As the system becomes more complex, there's more maintenance that needs to be done to support all the non-productive parts of the ecosystem. I'm a non-productive part of the ecosystem, right? I'm not adding any additional photosynthetic biomass, and yet I'm consuming that. So all the heterotrophs in that ecosystem are essentially drawing on the maintenance costs there. And so again, what you see then is a less additional energy for growth, but a highly complex and highly functioning ecosystem. And this transition point from the growth phase to the equilibrium phase is something that ecosystems have been able to deal with, and I mean, they have to. And it's something that, that I think human systems have not been able to deal with. That maybe will come out a little more in a few minutes. Okay, so we see this increase in complexity as order as a result of controlled growth. Again, how do we measure that complexity in terms of what was on that y-axis? assuming or working from this assumption that these environmental ecological systems are far from equilibrium, we can measure this complexity. I mean, like physics properties, we know it has to be a combination of both how much and of what quality, right? So we can't take just an extensive or an intensive variable. We have to take some combination of both of those. And maybe one of the ones you've seen in some of your textbooks is this IPAD equation, which Paul Ehrlich had put forward several decades ago now. Essentially, I is the environmental impact, and P is population, A is affluence, and T is technology. This came out of the debate in the 1970s when there was a lot of criticism of human population as being, the primary ecological or environmental driver. And I mean, it obviously is, but of course, one person in an affluent society like our own is using many, many more resources than somebody in other parts of the world where population might be higher. And so in order to recognize the criticism that it's not just numbers of people, it's also numbers of people times what those people are actually doing with the resources. And so here you see an extensive variable, which still is very much a driver behind that, but also weighted by the affluence and also the technologies. Through better technologies, we can lower that impact. Okay, well, in ecological systems, we've had a couple of who I would call pioneer researchers, people like Sven Jorgensen or H.T. Odom, EP's brother, or Bob Ulanowitz, who have also looked at different measures of looking at some sort of energy. So they know that energy is really the key idea in ecosystems, the key driving force, as opposed to population, and then times some quality factor. And so in each case, we've got an extensive and intensive variable. In exergy calculations, C is just the concentration of the biomass or concentration of energy, and the weighting factor is based on the genetic complexity of the organisms. In emergy analysis, E is the energy content, and it's weighted by a transformity function, which is based on the amount of solar radiation it actually took to generate that amount of biomass. So if you're higher in the food web, then you take more transformations. I can go into all of these in more detail later. I'm just putting these up here as some examples. And then lastly, Bob Ulanowitz, who is doing his work at Chesapeake Bay largely, was looking at the total, looking at a network approach. So I'm partial to this. Was that TIJ is the total, the sum of all the total flows through the network, through the ecological food web, weighted by an organization of the network itself. So he was using information theory to try to understand the network structure of the food web. And so it's not based on just the individual compartments and the biomass features of those compartments, but on the network structure. Again, we can talk about those later if you'd like. Okay, and another key point I think is, you can never say enough, is the misuse of the term growth that we use all the time. So growth and development are different things. Growth is a quantitative increase, development is a qualitative increase. They are different. You can develop without growing and vice versa. So some of these goal functions that I just mentioned in terms of like exergy and emergy and ascendancy have also been put forward by other systems ecologists in terms of these are the things that have been proposed that ecosystems are doing over time, right? So they've been maximizing power. This dates all the way back almost a century ago, Alfred Lotka's work, and also H.T. Odom's work in the 1950s. In other words, there was an idea that what ecosystems are trying to do is increase the internal energy flow of the system, which can be measured as maximizing their through flow. That's what this last little notation means there. Sven Jorgensen's work was talking about maximizing exergy storage. So it was not about how much was flowing, it was how much was being stored within the ecosystems in terms of biomass, but also in terms of that quality adjusted biomass based on the genetic complexity. People like Schneider and Kay have proposed that actually ecosystems are maximizing their dissipation. They're trying to dissipate the gradients as quickly as possible as their driving function. Other people have said they're trying to maximize cycling, or they're minimizing the specific dissipation, which is the export per unit of biomass, the export per unit of storage, or they're trying to maximize their residence time, the amount of time that the energy can stay within the system through cycling and through other turnovers in order to delay the release of that useful energy that they have. We have a paper that published about 10 years ago in JTB, Journal of Theoretical Biology, that looked at 10 different ecological goal functions And what that work did was showing that these goal functions are actually all complementary. I know this is new for you guys, but these, as different as they all sound, are actually like looking at things from a different angle, but they're not like, well, if this one is right, this one had to be wrong. So what it was we saw these different researchers coming at this question from different angles and answering it in a correct but not complete way. And so you really need all of these different to get the full idea of what's going on, but they're actually complementary to each other. So that was some of the work that we had done as foundational work, but what I want to talk about now is how they're changing over time, how those different goal functions actually are changing through those courses of succession that I've referred to. And in order to do that, we're going to break that long successional chain down into 4 different stages. The first one is what we would call boundary growth, which is essentially just getting more energy across your system boundary. The next one is structural growth, which is taking that energy and building biomass, building structure with that. And so those are both clearly growth terms because something is increasing in the system. Then the last 2 stages are really development stages. One has to do with the network and the intricacies of the structure of the network. And the second one has to do with the information. And it could be with genetic information, but also just information and communication that takes place within the ecosystem. So if we're looking at it during those different stages of growth and development, one hypothesis was that the storage and through flow will increase during all the stages, but the exergy degradation increases initially and then levels off. So in other words, we now can put some sort of axes here, something like exergy captured per unit biomass, we see will increase initially, but then we think level off during the later stages of succession, during those later stages of development. Okay, well, how do you actually test for something like this? There's really not long-term data to look at a system changing over a 100-year period. So one surrogate of that, speaking of what do modelers need from data, we would love to have a 100-year data set of how all these variables change over time in one place. But what people had looked at is different places that could represent essentially different points in time or even different types of systems at different stages. So what this is showing is the different types of ecosystems here and the amount of energy or exergy essentially that is being used by them, and then how much exergy is being stored, in other words, the biomass complexity factor there. So what you see is that if you've got a very simple system, like a quarry is basically reflecting most of the heat off of it and not absorbing it, same thing with the desert, so very little of that energy is actually being used because it's immediately being lost back to space again. A clear-cut forest is maybe absorbing about half the energy, a grassland maybe a little bit more. By the time you get to a forest ecosystem, it's capturing about 70% of the energy. It's never going to get to 100%. 70–80% is what most of the empirical data are showing, regardless of whether it's a plantation or a natural forest or old deciduous forest or tropical rainforest. However, notice that the amount of complexity in terms of exergy storage actually continues to increase. Obviously, a sharp increase during the early stages, but then as you go here, fir plantation is actually quite a simple system as far as the ecological variables go. So it has the same amount of energy being captured, and that's probably why companies like it, because you're capturing a lot of energy, but you're keeping it as a very simple controlled system. Whereas the tropical rainforest has quite an extensive amount of biomass and complexity information. So you essentially recreate this curve that we were kind of anticipating to start with. One of the ways that they actually measure this, just to show you something empirical here, is through these infrared satellite or just remote sensing images where this is a forest area, and you can see the clear-cut areas are showing up hotter, right? Because there's less of it being absorbed by the ecosystem, more is being reflected back into space. And so you can see temperature differences by looking, and you can get a measure then of the ecological complexity based on the temperature of what's left behind, essentially, how much is being absorbed and used by the ecosystem. Okay, the other way that we were testing it, this is back to my my training was actually in ecological network analysis, so whenever I can put things in terms of network language, it makes more sense to me. And so what we did was we built a simple network model of a toy ecosystem, and there are only 4 compartments, and it's essentially just a cycle here. We've got input only into the first compartment. We've got losses from each compartment. And what we do in these different stages to represent these different growth and development stages, first thing we do is we double the amount of boundary flow. So we say, what if the ecosystem has twice as much energy available to it? Well, what happens is that the flows all double. It's just a linear proportional change there. So that's not really such a big deal. It's expected. But what's really kind of cool is that if you add an additional link, so here we still have 10 units of energy flow, so it's the same amount of boundary available flow, but by adding an additional link here, you actually end up increasing the net sum of the through flows of that system. So the network change is providing an increase of the total system through flow. And so it's allowing it to keep that energy in there a little bit longer by having a little more complex networks and more cycling going on there. And so that's really not necessarily an obvious result. I think that's we were excited to see that. And then the 4th stage of growth and development is the information, right? So we go from network development to information development. And what we're modeling here is essentially an improvement in the functional behavior of 2 of the compartments. I think it was X2 and X4. We said, what if they became more efficient? Something changed biochemically or genetically, that they became more efficient at processing the energy. Obviously, if there's greater efficiencies, they keep more energy in the system. And so, no, it was actually, it was 1 and 3. So you see there's less loss from 3.6 to 2.1, which means there's more available in the system. So they did something to improve their efficiencies. So through information gains, they are now able to give the whole system benefits of having more energy available, right? So, and again, it's this indirect network connections that a benefit one place actually helps the entire system. So summarizing those results, through these 4 different stages, the boundary growth stage, and then the network stage, and then the information stage, we see that each of these different goal functions that we were looking at, specific entropy, energy through flow, exergy storage, exergy degradation, and retention time. So numerically, those are the changes. And it's kind of too much, but I mean, just to show you that there are numbers behind each of these changes, the summary slide is essentially this, that the specific entropy term doesn't change during those first 2 phases of growth and development. So the goal function is correct, but really only at the later stages of development when you get this specific entropy meant that the amount of dissipation per unit biomass decreases, but not at those early stages. Exergy through flow, on the other hand, energy through flow increased through all 4 stages. The amount of dissipation or degradation increased initially, but then actually became stable after that, so it doesn't change as you increase networks and information. The total biomass or exergy storage increased. Retention time also was flat the first 2 periods, and then only increased on the last 2. So based on these results, using the network model, even though all of those different ecological goal functions are correct at different stages of development, and they are complementary to each other, only the 2 of them, the energy through flow and the exergy storage, are really going to be occurring at all stages of ecosystem change. Right? So kind of the take-home message is, if you don't know what stage your ecosystem is actually in at that period, you should use one of those goal functions, because you'll most likely see a change. If you're at the early stages and you're using this as your goal function, you won't see a change. You'll only see it at the later stages, and so forth. Right? So there's the other ones. The 2 seem to be the most universal, I guess, through all stages of succession. Okay. I hinted at this, and to just kind of bring the story to some more recent work, is that this logistic growth model is not complete, because we know there's going to be a disturbance, right? We know in the long run there's going to be some sort of catastrophe or collapse. So really, even though we've been trying to track these ecosystem orienters along the development lines, we also know there's going to be a disturbance. And the question is, are they going to be able to continue along the previous development line, or is there going to be some sort of new system state that is kicking in and taking over there? So we have to amend our model to explicitly include the disturbance factors that we know are coming. So as I said, this logistic growth really only captures part of it. So the first part that I've mentioned, these goal functions, were looking at this axis over this time frame, or this system function frame. And this had been extended by Buzz Holling's work in systems ecology using this four-stage model. Maybe some of you have seen this before. I think it's very important work because he's essentially saying you explicitly have to include the destruction release phase and then also the reorganization phase. So it's a cycle. And it's more natural to put ecological things in terms of cycles. So the system reorganizes. It either is going to be able to repeat its pattern previously if the conditions were similar enough. The forest may regrow as a forest after a forest fire, or it may kick off here, and there's this little escape clause there, escape hatch, where it may become a different system. Maybe it was too much erosion during the extreme event such that you cannot get a forest to regrow there again. So there's this recognition that you might not always get the same system back again. Okay, so we slightly modified Buzz Holling's figure in this form. So this is the one we hope people see in the future. I mean, this is classic already, I think, and hopefully you have seen this. So we modified it so that you see now that there's a monotonic decrease during the collapse phase. It kind of didn't make sense to have it going back up again, other than for aesthetic reasons. Buzz has said that himself, that it just looks good as the figure 8. But he agrees that this model is probably a little more accurate. Also, it shows the kind of squiggly patterns going upwards, that there's always going to be some smaller scale disturbances, but there's still a larger trajectory that you can model out of that. So the trend, unless that big disturbance comes, the trend is still going to be holding. Okay, and the other message of this model is that the collapse phase is not necessarily a bad thing, and we take this work from Joseph Schumpeter in economics, who referred to this as creative destruction, which kind of got a bad label during the last economic recession because they were, I think, misusing what it meant. But essentially the idea is that when you have a collapse phase, that allows for new things to emerge. When you have a not static, but if you have a system that is fully taking up the space, you don't have room for new innovations and opportunities in there. So within economics, they recognize the need for these periodical disturbances in order to allow new opportunities. If you're interested in these collapse ideas, I really recommend Joe Tainter's book on the collapse of complex societies. You may have read Jared Diamond's book on collapse, which is nice stories about collapse of different societies, but Joe offers a very nice theory on why it happens, and it's actually predates it. It's 1988. So one of the better books out there on this topic. Because then the other thing that you can consider is that during the collapse phase, so I've shuffled the axes now, this is development potential. At the beginning of the system, when you've got just the open field, you have the most potential, right? The potential is highest, and the potential actually decreases during the entire development period. So it's only when you have the collapse that allows you to reset and then to basically wipe the slate clean and to essentially allow for something else to develop. Now I'm starting to get the ecological observations into human system metaphors, right? I'm working into what we're doing with our systems, with socio-ecological economic systems. And so there's kind of a blurring there, but I'm taking from what we observed in the ecological systems and seeing if it makes sense elsewhere. So over some long term, we might see something like this. Each collapse phase is then allowing for a new initiation of that long-term trend, which probably is getting a little bit better. Maybe this is just our human mind, and we're progressivists in the sense that we always think things have to be better. We can discuss this, because I'm still not sure I agree that that this is the right long-term model, but I do agree that there's a collapse and then it allows something new to come up. Okay, yes. A lot of this is put together very nicely by a colleague of mine, and I'm referring to this as a synthesis model now. So this is really taking it to the human domain, and so we've got our 4 different phases here, and you're talking about, okay, during the exploitation phase, there's growth taking place, there's adaptation, there's gathering resources, and then up here you're in the conservation phase. Things are stable, you're at a high level of performance, but then things become set, stable, rigid, and then, oh no, there's a shock, and then the first response is always, oh no, collapse. but then, the hey, new opportunities, new connections, trying other things, hey, this might work out, and entering a new growth phase. And so this is the kind of model that we're working with now, is that recognizing the goal of a system is not to just keep it in one stage forever at this high level. Then you just become too brittle, and then the collapse becomes actually worse. It's allowing and recognizing and working within these longer term dynamics, I think, is what makes the most sense. So, okay, and then wrapping up, ecological systems are open systems that use resource inflows to increase their complexity and move further from thermodynamic equilibrium. We do have some orienters that we think can track this dynamic development phase, but we also know they go through a complex cycle that includes the growth and development as well as the collapse and reorganization, and that collapse is not necessarily a bad thing. It's a normal response to the long-term dynamic. And where a lot of my own personal research nowadays is, as I was hinting at, is taking our understanding of ecosystem dynamics, design, and function, and seeing if we can say something useful to our design and management of human systems. So some of the areas for future research are, and just more generally in ecological modeling, to give you a sense of where our community is. A lot of work in individual-based models seems to be very hot right now. Again, looking at social, economic, ecological models. So the ecological part is part of a larger integrated model where we're including economics and other social factors. Obviously, spatially explicit models and land use change models, and climate factors are, again, a big driver right now, and other biogeochemical cycles and all the traditional stuff. Some of the stuff we actually think we've been doing pretty well for several decades now. So, okay. Thank you for your attention. That's not the view from my window. Those are the Austrian Alps. But it doesn't look that much different. I was quite impressed with that. And one last little plug, I have a book with some colleagues coming out in July. You can read that, Flourishing Within the Limits to Growth. It's actually a follow-up on the original Donella Meadows et al. Book on limits to growth, looking at some of the ecological principles in terms of how we could flourish within these limits, accepting them but flourishing within them. So that's all I have.
Just a quick question. I was wondering, for your book at the end, is that organized in a way that's suitable for teaching courses, or?
We would like to think so. Yeah. I mean, it wasn't written as a textbook, right, with problems or with exercises. But for a seminar class or for a class that's talking about sustainability issues, I think that it would make a good companion. Because again, what we're trying to do is outline what we think some of the ecological principles are, and we recreate the Meadows et al. World model, but now incorporate some of the ecological principles into the model and try to find scenarios which are viable scenarios.
Trying to look at it in a forward-looking thing when it feels so much like collapse is really a big deal, and it seems like you're actually accomplishing that.
Yeah,
which is very nice.
Trying to. Thanks.